say that 1 and I are two different bases, and each have dimension 1.
Okay. So let us look at. So first, let us look at. First, let us look at the basis question. So, basis is not unique. Okay, so let us take a familiar example. So let us say that I have three-dimensional Euclidean space, that is R3.
So you're not presenting. Your presentation is not this.
Am I presenting now?
Yes, sir.
So if you consider this space R3, which is basically a set of vectors like this, x, y, z, such that x, y, z in R. Okay, this is a three-dimensional Euclidean space that is familiar to us. Now, for this, if you say basis, our standard basis is this unit vectors, right? We call it as I cap. And now this I cap can be written as 1, 0, 0. J cap is 0, 1, 0. And K cap is 0, 0, 1. Now, tell me, this is a basis. There are three elements in the basis, correct? Now, what should be three vectors? How did we define the basis? We defined the basis as set of maximally, the maximal set of linearly independent vectors. Okay. Suppose if I consider another basis. So let us consider another basis. Okay. So basically, any three linearly independent vectors can become a basis. So let me say I plus j. I and I plus j are linearly independent. And then I plus j plus k. I plus j plus k. So suppose if I take these three vectors, that means these three vectors are 1, 0, 0, 1, 1, 0, 1, 1, 1. Of course, these are not normalized, but that is okay. So these are three different vectors, and these are linearly independent. So this is another basis. But the number of elements in this basis or that basis, that has to be equal, same. So dimension of the vector space is unique. Okay, dimension of vector space is unique, but basis is not unique. It's not two different bases. You can have infinitely many bases that is defined, that can be defined. Okay, so the basis choice. Earlier, I made a comparison that choosing a basis is like choosing a coordinate system. You can choose your coordinate system in infinitely many ways. So that way, your basis is non-unique, and there can be infinitely many ways of choosing the basis because it is just set of three linearly independent vectors. Okay, so that is what I said earlier with respect to this question. Now the second question, I think what you asked is with respect to set of complex numbers. So my vector space V is the set of complex numbers. Now there are two things. I think A over real field over a field of real numbers. R. And then B over a field of complex number. Now, first let us try to understand the dimension of a vector space. Okay, so dimension of a vector space in the case of A. So I told you that to decide on the dimension, we have to ask the following question: what is the field here? Field is set of real numbers. Okay, so that means how many real numbers are required to define a complex number. How many real numbers are required? You require two real numbers. One for the real part and other for the imaginary part, right? So A plus IB. So you require two real numbers, right? So what should be dimension of V in this case? Should be 2. The number of fields or the number of scalars required to define an arbitrary vector. Now, once you know this, you can say that, suppose you want to know, ask what is the basis. Okay, so the basis can be defined as 1 and I, because you multiply this with 1, A with 1 and B with I, you get this. So then there are two elements in the basis. Okay, this is 1 is a complex number, I is a complex number. So 1 and I are the basis elements. Now let's go to B and ask the same question. How many complex numbers are required to define a complex number? You take only one, no? Same complex number you can choose. Okay, so the dimension of the vector space, when you define our set of complex numbers, it is simply 1, because the same question, a similar question, if you ask here, you say it's 1. One complex number is required to define 1. So what should be the basis here? So basis is simply 1, because you take the same complex number and multiply it with 1, you will get this. Okay, so why I am asking this question is that I want you to appreciate that. So the point that I want you to appreciate is the following, and I think some of you might have appreciated by doing this exercise. You have a vector space V. Now you have a vector addition plus, then you have a field. Okay, so this is what it is. Now whether V becomes a vector space or not, okay, V becomes a vector space or not, depends on all these three things. Okay, suppose if I say that I have so if I change any one of this, then the vector space is not same. Like here I said you have set of complex numbers, so my complex number with addition and real, this is a vector space, no doubt, but it is a two-dimensional vector space because I require two real numbers. Two-dimensional linear vector space. On the other hand, if I take complex number plus with complex number, is simply one-dimensional vector space. And it is, so this vector space is same as real number plus with real. Okay, real with real is only one-dimensional vector space. Complex with complex is also one-dimensional vector space. Okay, so that is what I want you to appreciate, that if I change either the field or the binary operation, then the vector space is different. It's not the same vector space. Okay, so I hope that clarified. Adra?
Yes, sir. Thank you, sir. I understood. Thank you.
Yeah.
So, one small
Yeah.
doubt is that
Yeah.
can the basis of one act as a basis for the second example? Because we can't, using just one, we can't create a complex number. But if I was there instead of one, then we could have created a complex together with this real.
No, you can see what I'm trying to say is for complex plus complex. The field is complex, no? So suppose I want, so let us say, let A plus IB is a general element of C. Okay. Now, since the field is C, okay, we take A plus IB from the field. And multiply with 1 to get the general element. It's exactly like real with real field, right?
Got it.
Yeah. Now, I just want you to think about this case. It is probably not written in that set of examples. So we know that set of rational numbers okay, we call it as Q. No, set of rational numbers Q is a field. Okay, so this you can prove it. Okay, set of rational numbers is a field. Okay, so this Q is basically set of all P by Q such that Q not equal to 0 and P, Q are integers. So this is set of all rational numbers. That is a field. Now let us say that define set of real numbers plus, but the field is set of rational numbers. Okay, that means this is so basically what I'm saying is set of real numbers is basically set of vectors. Okay, and defined over a field of rational numbers. Okay, so the question is it a vector space? Okay, so if so, what is the dimension? If not, which axiom does it violate? Essentially the same thing that I have written in that problem sheet, but this is essentially a different example. I don't know, I don't remember if this is there yet. Maybe it is not. Okay, so please try this. It's interesting to work on this example. Okay. So any other question? Okay. So,
hello, sir.
Yeah.
Sir, can you once again teach about some operations about inner product, like u bar v is equal to v bar u star?
Okay. Okay. So let us try to recall some of the things that we have done yesterday. So let us say that so we have understood everything about vector space. So we can say that we have a vector space. So V is a vector space. Okay, so I'm going to over V. So I'm going to, so from now onwards, unless I specify, my field is always complex numbers. Okay. So vector space over complex numbers. Now I'm not going to also tell you what this vector space is. Okay, V is a vector space over complex numbers. Now what we are going to say is that, so there are two things that we have, two types of vector spaces that we can talk about. One is this vector space can be finite dimensional, or this vector space can be infinite dimensional. We know what is the dimension of a vector space. We can have finite dimensional vector space and infinite dimensional vector space. Now let us quickly recall finite dimensional vector space. So what we have in finite dimensional vector space, we can have several examples. So let us say that dimension of vector space is equal to some n. Then a vector V in this vector space V, okay, a vector, this is an element, okay, so an element or a vector. Okay, so we represented with this ket, right? So this is an element or a vector, is in V. Now, if a basis is chosen, then in that chosen basis, I can write this V as a column of components, V1, V2, etc. from Vn. Because this is n dimensional vector space, there will be n components. Okay. Now I can define. Okay, so define a linear functional denoted by a bra vector on V, where this V can be written as V1 star, V2 star, etc. Vn star. Okay, so as we have seen last time, this is equal to this vector transpose and conjugate. Okay, so this we will call it as V adjoint. Okay, transpose conjugate in in one particular symbol, we say this is adjoint. This is called V dagger. Okay. So we have this one such that when V acts operates, when E operates on an element of V, we get a scale. In this case, a complex number. Okay. Now we can say for some U comma V in V, okay, we can define U as U dagger, then this becomes a linear functional such that this U V is a complex number. U V is a complex number. And this one we will call it as an inner product. What we call as an inner product. Now in the chosen basis, this inner product can be defined as sum over j is equal to 1 to n uj star vj. So in a chosen basis, in terms of components, this is what this is, and this is basically you have this u1 star, u2 star, un star, and this row is multiplied by a column v1, v2, etc. vn. So this is what I wrote in shorthand as uj star vj star summation over j equal to 1 to. Okay, so this is called an inner product. Now, I also said that the set of all linear functionals, form a vector space. The set of all linear functional form a vector space, which we denote. I don't know if I denoted it as V tilde earlier. We denote V tilde. And we call V tilde as a dual of. Okay. Now, if V tilde is same set as V, we say that V is self-dual. V is self-dual. There are some cases where V tilde is not same as V, even though it's not very, I mean, you have to look carefully to find out those examples. I want you to understand this a little carefully, and let me tell you one very uncommon example which you might have, you might not have thought it as this. You know, in crystallography, you have this. For example, if you take a body-centered cubic lattice, okay, it is one of the 14 Bravais lattices. Now, each point, if you consider that is like a vector, you can talk about a vector space. Now, the dual of body-centered cubic lattice will be face-centered cubic, and face-centered cubic's dual will be body-centered cubic. And the abstract sense of this dual is interpreted in solid-state physics as direct lattice and reciprocal lattice. So essentially, the reciprocal lattice is like a dual for the direct lattice. So the same concept is used in a different way there, but these are all connected. Okay, so that is one simple example I can give you, but there are more complicated examples, which I will mention some of them as we go along. Okay, so this is how we define the inner product. Okay, so we now have, that is, you have V is now called an inner product space. V is now called an inner product space. Okay. So this is how we define this inner product, and then we have said that if you consider V with V, okay, so if you consider this VV, inner product of V with itself, okay, so this defines the norm of vector. Norm of vector V. So basically, the norm of vector V, which you denote it as something like this, this is equal to square root of V. So the mod square of this one will be equal to V. So you can define the norm of a vector once you define the inner product. Okay. So this is, that means if you think in terms of a chosen basis, this is going to be sum over j is equal to 1 to n modulus of vi the square. Okay, so this is an under square. Okay, so that is the norm of this one. Okay, so this is as far as the definition of inner product is concerned. Now we are, yeah. So now we have the next thing, that is, let's say that we have infinite dimensional vector space. Okay, so infinite dimensional vector space. We have infinite dimensional vector spaces. Now there are two types of infinite dimensional vector spaces that we can think of. Okay, so they are, so as we have seen, that there can be countable infinity, are uncountable. Okay, so first let us look at an example of countable infinity. Okay, so now let's say that we have a vector space V, okay, which will be a kind of sequence of functions like this. Let's say V1, V2, and so on. It goes on and on and on up to infinitely many terms, such that all these Vi are complex. Okay? All these are complex numbers. Now so the problem is that this is a vector space of infinite dimensional vector space. There is no problem. But now, can we define an inner product? Okay, so to define an inner product, we require a property. Okay, so these are discrete elements, but infinitely many elements. So suppose, so let us say that I have some u and v, let's say two vectors in this vector space, and I want to define an inner product. Okay, first consider this. Consider the norm or the magnitude of v itself. That will be simply sum over I is equal to 1 to infinity vi mod square. Okay. Now we have argued that if it is each one of this is positive, and if I have sum of infinitely many positive things, then it is going to infinity. Okay. So this one goes to infinity in general. It goes to infinity in general. But now let us say that we will choose this sequences such that, okay, so I'm going to choose now a different set, not all possible infinite dimensional vectors like this. Okay, so I'm going to choose choose those vectors such that those vectors, let us call that vector as some phi. Those vectors phi such that this phi is less than infinite. That means it is finite. That means I'm going to define a vector space such that I have phi 1, phi 2, etc. It's an infinite sequence of numbers that each one of them is a complex number, and sum over I is equal to 1 to n, 1 to infinity. Modulus of phi I square is less than infinity. Okay, so this is a vector space, and we define this vector space as L2. Okay, what is this L2? This is called square summable. Square summable space. Square summable space of, because this phi 1, phi 2, phi 3 are sometimes called sequences. So it says square summable space of sequences. If you define this one, then there is no problem, because the norm of every vector is less than infinity. That means it is some finite number. And if you want to normalize it to 1, you divide this vector by that number. So the vector by square root of that number. So that is how you can normalize. So if you have an infinite dimensional vector space where it is countable, you can define an inner product for only those vectors that are square summable. If they are not square summable, and this inner product will not be useful, because that will go to infinity. So if you have a set of square summable vectors, then for that you can define an inner product. Okay? You can define an inner product. So this is the infinite dimensional vector space. Now let us look at other uncountable infinity. So uncountable infinity is what we call as functional spaces. Okay, functional spaces. So some of the vector spaces that we have talked about. Okay, so let's say I have a V, which is set of all functions f of x, such that f is defined from some closed interval a b to, let's say, complex numbers. Okay, so I have set of all functions such that f is defined from closed interval a b to complex numbers. Okay, so this is a vector space. There is no doubt. You can prove that this is a vector space. Now we want to define an inner product for this. Okay, so I'm not going to repeat that heuristic argument that I have shown you last time. From I have borrowed it from R. Shankar's book. So, but I will simply say that if you have some f of x and g of x, let's say these are two different functions in this V, then we can define the inner product of these two functions. I am going to now denote this with some bracket, f of x comma g of x. Okay, so this notation is slightly different, but we will go back to that notation from this notation, and for that we will invoke Dirac. Okay, till that time I did not bring Dirac, but to go from functional space to bracket notation is what Dirac has suggested. But we will go back to that. But let us define like this: f of x into g of x. So that is equal to integral from a to b f star of x into g of x dx. This is the definition of the inner product. Okay, and in order to come to this definition is what we have given that heuristic argument given by Shankar. So the norm of f of x is defined as simply f of x inner product with f of x. Okay, so that is equal to integral a to b f of x mod square into dx. Okay, now you can say that this is fine, but if your f of x is such that this integral goes to infinity, then again this norm will be this is not a good space. I mean, this it's exactly like in the previous case, right? If all the sequence is going to infinity, so we say that we will not take all this vector space, but we are going to define our set of vector spaces. Now I will call this as capital L2, and it is usually written as capital L2 of AB, which is equal to set of all functions f of x such that this f is defined from a to b, ab to complex numbers. Okay, AB to complex numbers, and integral A to B mod f of x the square dx has to be less than infinity. Okay, so this set is called set of square integrable functions. Set of square integrable functions. Now, please note that this particular space. Okay, so now consider a situation like this. Okay, so let us back to physics for a while. Back to physics. Now consider a particle. Okay, so consider a particle in the region A less than or equal to x less than or equal to b. Okay, so let us say that this is like some kind of a molecule, a linear molecule of length b minus a, and let's say there is an electron which is free in this particular molecule. That means it can be anywhere, but it cannot come out of this molecule. Usually this is something which we are familiar in chemistry, right? There are free electrons, but they don't come out of the molecule unless you you kick them out by ionization or something. So otherwise it is like a free particle. Okay, so now quantum mechanically, let us say that so let some psi of x be the wave function for the particle. How do we know that? We will solve Schrodinger equation and get this as a solution. So psi of x be the wave function for the particle. Now what we know from Bond's thing is that psi of x mod square, psi of x is a complex valued function in general. So psi of x mod square into dx, this is defined as the probability that the particle is located can be located between x and x plus dx. X and x plus dx. Suppose if this is your x and then there is a small deviation dx. Okay, so in this region, what is the probability that you will have the particle? That is given by this. Okay, now there is no point in talking about this particle if the particle is not there in this entire molecule, right? So probability that the particle is in the region A less than or equal to x less than or equal to b is given by integral A to b mod psi of x square dx. Okay, now so if we are saying that this is my molecule and particle is in this molecule, then I must I must ensure that this has to be equal to 1. Okay, so particle should be there in the region. So that means total probability should be equal to 1. Okay, so physically we demand that A to B psi of x mod square dx should be equal to 1. This is total probability. So this has to be interpreted as total probability. And total probability has to be always equal to 1 in the entire regime. Now, if this has to be equal to 1, okay, so for this to happen, okay, we need integral A to B modulus of psi of x the square dx should be less than infinity. Okay, say integral A to B psi of x modulus square dx is equal to some n which is less than infinity. Okay, then we define some psi tilde of x is equal to 1 over square root of n into psi of x, such that integral A to B psi tilde of x modulus square dx is equal to 1. Okay, so here psi tilde of x is called normalized wave function. But what is the requirement for normalization? If you want to normalize it, at least it should satisfy this condition. That means it should be square integrable. Okay, so square integrability. So note that square integrability is necessary for normalization. Okay, now because of this, what happens is that for any quantum system, the state space has to be set of square integrable functions. Okay, so the state space thus the state space of a quantum system has to be L2 space. L2 space is what? That is the space of square integrable functions. Space of square integrable functions. So you can see that L2 space is a vector space, L2 space is an inner product space, and we require L2 space to determine the space of state space of quantum system. Okay, that is what we require because we should normalize the wave function in order to state that the total probability is equal to 1, and normalization requires square integrability, and hence the state space has to be a set of square integrable functions. And if you have some boundary conditions, it will be a subspace of this state space, this L2 space. But L2 is an absolutely necessary condition. Okay, so this is what is the motivation to consider this L2 space.
Sir,
Yeah.
can you define us about the probability density also, sir? The difference between probability and probability density too. That the whole idea is complete.
Yeah. So essentially, at this point you can say that as I have defined here, so this quantity is the probability. Okay. So if this quantity is the probability, my modulus psi square is called the probability density. Probability per unit length. In one dimension, it is unit length. In three dimensions, it is unit area. And this is what is called probability density. Okay. So many times you will get some questions in the interviews, like what is the dimension of the wave function and things like that. So that is, you can say that the probability has to be dimensionless. Okay. So the question generally asked is, what is the dimension of psi of x? So you know that modulus of psi of x square into dx is dimensionless. Okay, but this has a dimension L, right? So psi of x mod square into dimension L is dimensionless. Is some constant, let's say 1. So psi of x has got 1 by L to the minus half. So this is the dimension. Okay, so it has dimension because this is related to probability amplitude, and in 3D, in 3 dimension, your psi of r will have a dimension of 1 by L to the power minus 3 by 2. That is 1 by volume to the power minus half, which is basically L to the power minus 3 by 2. So this is sometimes in interviews people will ask whether you have thought about it or not. Okay.
Excuse me, sir.
Yeah.
Sir, I have one doubt, sir. Like when we normalize any vector, like vector element of belonging to vector space in order to bring the probability to 1. So what we essentially do, like do we modify vector element, or like we do some kind of change in vector space itself? Like what does that normalization means? Actually, I couldn't understand this.
Okay. So in general, normalization is, see, suppose this is something like that. Suppose if you have a vector, let's say v1, comma v2, comma v3, a general vector. Okay. So what do we say when we, let's say this is a vector v. Okay, I'm writing a general vector notation. So when I say that I'm going to normalize this one, that means my magnitude of this vector has to be equal to 1. So when do I get this? When I take this, okay, let us call this as v prime. Okay, so I define my v prime in such a way that it is v divided by modulus of v. Okay, so if I write v divided by modulus of v, then I have, so what am I doing in doing this? I'm actually, so what we will call this one, okay, v prime, so let's call it as v prime. We will call this as a unit vector, right? This is a unit vector along the same direction. So I have some direction I mean, going back to direction magnitude, let's say this is my vector v. Now there I am going to find out a unit vector. Okay, so unit vector is the normalized vector. The same concept is generalized. When I say I have a normalized wave function, that means it is like a unit vector in that direction. But here the direction is something which we have to imagine, because you have infinitely many directions. So that means you can have a particular direction. In that, when I say I take a normalized direction, that normalized eigenstate, a normalized wave function will describe that the unit vector along that direction. So it is like that.
Okay, so
Normalization is just like finding the unit vector.
So the idea is like we are trying to find the unit vector of that vector element belonging to the vector space.
Correct, correct.
Okay, thank you.
Sir?
Yeah.
Sir, this is like something which I had in mind. Like, if you go a little bit backward, we have seen that square summable space, isn't it, sir? In that, you say that the ones which are in square summable space are the ones the series is summed up to less than infinity, isn't it, sir? So it is something like when we take some geometric series or arithmetic series which has some radius of convergence. So the series which
Correct.
doesn't converge will not be a part of this space. And the same thing
Exactly.
goes with the integrals. It is something like the improper integrals which diverges will not
Yeah.
be in this space. And
Correct.
when we do an integration test, so those will be a part of this space. So this
Correct.
is what I had in mind, like a connection between this mathematical structure with this vector space. So is it right, sir? What I said?
Yeah. Yeah. That's correct.
Yeah, okay, sir.
Okay. Now, okay. So if you look at our discussion so far, we have considered. When we talked about a functional space, then we initially started with some set of all functions defined from A, B to C. And like what I discussed in the last time, we have been able to generalize the definition of inner product such that f of x, g of x inner product is this integral f star g dx. From there, we can define the norm. Now, I want this norm to be finite. Okay, so if I put in that additional requirement, then I get L2 space, which is a subspace of this V. Okay, it will be a subset of this V. Now, this is called set of square integrable functions. Now, what I'm trying to say is this set of square integrable functions that we have is very relevant in physics. And that is why I've come back to physics and I said, suppose if you have a particle in this region A and B, and then let's say that the particle is represented by a wave function psi of x, then the interpretation is that this mod psi square dx is the probability that the particle can be located between x and x plus dx. Now, if that is the probability, and if you ask a question, what is the probability that the particle is there between A and B? It has to be 1, because if the particle is not there in that molecule, there is no point in studying about that particle. So we have to make sure that it is there between A and B, and that can be made sure by taking a state which is normalized. That means which can be normalized. If it is not normalized in the first place, we can at least normalize. So the normalization is possible only if it is square integrable. So square integrability is an important necessary condition for a state to be, for a function to be represented as a quantum state. So once you know that it is square integrable, then you can normalize by dividing that wave function with the square root of the value of that integral. And that is called the normalized state, and the normalized wave function will be, it is not only square integrable, but the value of the square integrable thing is equal to 1. Okay, so this is the motivation for us to. So what I am trying to state here is that the state space of a quantum system has to be an L2 space. I mean, it has to be L2 space at least. That is the space of square integrable functions. Okay. Now let's try to ask the following question. Suppose you consider, so let us try to go back to this example. So let's go back to mathematics. So get back to so we have defined. So consider set of all polynomials. Consider set of polynomials. We have shown that this is an infinite dimensional vector space. Okay, which is an infinite dimensional that we have already seen. Okay. Now you can say that suppose I take any two polynomials, or I take any polynomial, for example. Okay, so let P of x be a polynomial. Okay. Now I try to ask what is the product, I mean the inner product of P of x with itself. P of x with itself. That is equal to, polynomials are generally defined from real line to let's say to complex also, because you can multiply this with the complex numbers. So I can say that it's minus infinity to infinity, and P of x mod square. Now notice that in general, this kind of a polynomial, when you do this, it is not square integrable, because for square integrability, this P of x has to fall faster than 1 by square root of x. Correct? Then only it will be square integrable. Okay, so I think, I don't know if you can view this. So for a function to be a function, let's say f of x, to be square integrable, we must have f of x going like 1 by f of x decaying faster than 1 by square root of x as x goes to plus minus infinity. Asymptotically, it should decay much faster than this. Okay, so I do not know if it's easy to think, but think about it. And try to prove. Okay. Now, but polynomials are obviously not going like this. Polynomial unit is like x square, x cube, and things like that. So this goes to infinity in general. That means the polynomials are not square integrable. Okay, the polynomials are not square integrable. Now you can ask a question that when can they be square integrable, or how to make them square integrable. Okay, so that means what? The polynomials, that is p of x, is not square integrable. That means, can we not use polynomials as quantum states at all? Okay, so does it mean polynomials cannot be used as quantum states? Okay. Answer is no, because you can use polynomials in two situations. Okay. So we can still use. We can use. This is the answer. With the two in two cases. Okay, we can use. First is if the polynomial is defined in some finite interval. Okay, so that is when defined over finite interval. That means I don't have minus infinity plus infinity, let's say, but I have AB. So if I have AB, then it will not go to infinity, because the interval is finite, and hence you have this integral is still a finite value. Okay? This is the first case. And the second case is that even if you have infinite interval, by generalizing the definition of inner product. Definition of inner product. Okay, how are we going to define? So we define this. Define your, let's say, pi of x. This is a polynomial pi of x and pj of x. Okay. So I'm going to define this as integral, let's say, minus infinity plus infinity. I am going to introduce some w of x into pj star, pi star of x, pj of x. Earlier in dx, earlier we did not have this w of x in the definition of inner product. Okay, so where this w of x is a weight function, such that w of x is greater than 0 for all x. It will be some function. Now, depending on the polynomial that we have in mind, we can choose this function such that it will be still made square integrable with this definition. Okay, so this is another way in which we can generalize and then bring these polynomials into the possibility of using them as quantum states. Okay, so you will see that with these definitions or generalizations, we will have occasions to use Hermite polynomials, Legendre polynomials, all these special functions that you might have studied in your mathematical physics 1. They all will become members of quantum states with this definition or modification to the definition of an inner product. So this is another way in which we can generalize the definition of an inner product. So that is so much for the inner product and the inner product space. Now we can say that we have talked about vector spaces extensively, and we talked about inner product spaces. Definition of inner product with respect to now with this inner product, I have defined. So I have defined a normalization process. That is, if you have a square integrable function, you can normalize that function. Now we can say that so this is this modification in terms of the polynomials. Now we can ask a question that so let's say that now I have my V. Now this V is now an inner product space. Okay, so I have an inner product defined on that. So V is an inner product space. Now let's say that I have phi of x and psi of x are in V. Okay. And then I will define phi of x comma psi of x as their inner product, right? This is the inner product. Suppose if it is equal to 0, which implies, or this implies this also, if it is 0, then we say that phi of x is orthogonal to psi of x. Phi of x is orthogonal to psi of x. So the way you define orthogonality is by simply look at their inner product. If the inner product is 0, then they are orthogonal to psi of x. So this is a generalization of this notion of perpendicular in our vectors with direction and magnitude. If two directions are perpendicular to each other, we say they are orthogonal. So this is basically, since inner product is a generalization of dot product, this is basically a generalization of the orthogonality. So this is another notion. Once we have defined inner product, we can define the notion of orthogonality. We can define the notion of normalization or find the norm of the wave function. Okay, and normalize the wave function. Okay. Now, once we have understood this, we can talk about a few interesting notions. Okay. So let us say that so once we understood this, then we will talk about something called completeness of the space. Okay, so this is called completeness. Okay. So this is a little hard concept, but let me try and see if I can put it in simple words. So let's say that so I have a vector. I have an inner product space. Okay. So consider a sequence. Consider a sequence of elements. A sequence of elements of. Okay. A sequence of elements of E. Okay, say say I have, let's say, phi 1 of x, phi 2 of x, etc. It's an infinite sequence of elements of A. Okay. Now, if phi m of x minus phi n of x, okay, phi m of x minus phi n of x, and the magnitude of this vector. See, phi 1 of x, phi m of x minus phi n of x is another function. Now, this magnitude of this function, how do you find out the magnitude? You have to take the inner product of phi m minus phi n with phi m minus phi n. Okay, so this is the norm, right? So the magnitude of this, or the norm of this vector, goes to 0 as m and n, both of them become very large. Okay, if this is the property of this sequence, then we call such sequence, a Cauchy sequence. Call that a Cauchy sequence. Okay. So you have a sequence. Now the sequence is such that so what does that mean? That means let us say that you have phi 1 here, okay, phi 2 here, phi 3 here. Okay, I'm just saying these are like a one-dimensional this thing. Then as you are going, so let's say you have phi n here, then phi n plus 1 here, okay, and so on. It will go to infinity. But what happens as you go to higher and higher n, they will become closer and closer. So they get clustered. Okay, so it is something like this. Let's say I have a sequence like this. Okay, as you go, it becomes closer and closer and closer, and it is clustering like this. So that means the difference becomes smaller and smaller as you go to higher and higher values. So this kind of a sequence. This kind of a sequence has a very interesting property, that since it is getting clustered and clustered and clustered, this sequence will actually have a limit point. Okay, so that means this sequence will have a limit point. Okay, so that is another thing. So every Cauchy sequence, has a limit point. What does that mean? That means there exists a function. There exists a function which I will call it as some phi of x, such that phi n of x minus phi of x in the limit n tending to infinity is 0. That means this phi n will reach this phi x. So phi of x is called the limit point. Phi of x is called the limit point, or limit function of this sequence. Okay. Now you can define this completeness in the following fashion. This is of course defined for a vector space. Okay. A vector space is complete if it contains limit points of all Cauchy sequences. That means you can construct different Cauchy sequences, and all those Cauchy sequences will have a limit points, and those limit points should be inside that vector space. In that case, we say that this vector space is complete. Now, it is a little tricky to do this. Suppose if you have a finite dimensional vector space, then it is not it's not very difficult to show that it is complete. But if it is an infinite dimensional vector space, the proof is not very trivial. Okay, so proof is involved in some sense. But I want you to get a feel for this concept. A vector space is complete if it contains limit points of all sequences. So just to give you some simple example, let's try to simple case. Suppose, let's say that it's not a case of vector space, but suppose let's say that I have an open interval 0, 1. Okay, so this is my set. So my set is equal to open interval 0, 1. Then I can have a sequence. Okay, so I define a sequence. So the sequence is simply 1 by n sequence. That means it is 1, 1 by 2, 1 by 3. So this is the sequence. Now, what happens in the limit n tending to infinity, 1 over n, this will go to 0. Okay, the sequence will go to 0. Right? Now, but 0 is not in S, because this is an open interval 0. 0 is not in S. So then what happens? This every member of this sequence is in S. Okay, that is every member of this sequence is in S, but the limit point is not in S. Okay, so sometimes it can happen like that. The entire sequence is in the vector space, but its limit point is not in that vector space. Then we say that it is not complete. But if you can contain all the limit points, okay, it contains limit points of all Cauchy sequences. Whatever Cauchy sequence that you can construct, its limit point should also be there in the vector space. Then we say that the vector space is complete. Okay. Now we are ready to define what is called a Hilbert space. Okay. So Hilbert space is called a complete inner product space. A complete inner product space. And what is an inner product space? It is a vector space in which inner product is defined. Okay. So inner product space is a vector space in which inner product is defined. Above that, if you have this completeness property, then what we call this as a Hilbert space. And L2, okay, the set of square integrable functions, okay, of a comma b or whatever, or L2 of r, or L2 of r, that means from the real line. Okay, so basically the functions are always defined from this whatever set that I am writing with L2 within this bracket to complex numbers. Okay, so they are examples of Hilbert space. Examples of Hilbert space. Okay, and finite dimensional vector spaces. Finite dimensional vector spaces, the completeness is always guaranteed, and hence all finite dimensional inner product spaces are Hilbert spaces. A Hilbert space can be finite dimensional or infinite dimensional. The completeness has to be worried about only for functional spaces. Finite dimensional vector spaces are, if you can define inner product, they are Hilbert spaces. Okay. So the ultimate understanding that we might have obtained, I am hoping that we have obtained from all this analysis, is that the state of a quantum system, is represented by a complex valued function psi of x comma p called wave function or probability amplitude modulus of psi of x comma t, the square dx is the probability that the system is located in region dx around x at time t. Now, set of all quantum states is a Hilbert space. Actually, this is what is called postulate 1 of quantum mechanics. Postulate 1. So I have spent 3 classes only to write this last sentence. Okay, the set of all quantum states is a Hilbert space. Now, for you to understand what a Hilbert space is, what last 3 or 4 classes that we have labored so much to define various quantities, to define various aspects, and now you understand what state space is. The state space is always a Hilbert space. Now, what is a Hilbert space? Hilbert space is a complete inner product space. What is complete space? It is a vector space that contains all the limit points of all Cauchy sequences. What is a Cauchy sequence? It is a sequence of elements of a vector space that close onto themselves as they go far away. And then what is an inner product space? An inner product defined on the vector space. What is an inner product? It is a kind of a mapping from it's a linear functional mapping a vector to a scalar. So we take one function, one vector from the dual and one vector from the vector space. We define a scalar, and then of course we have vector spaces. Vector spaces are finite dimensional and infinite dimensional. So all this discussion is actually I have done all this discussion so that if I write this one paragraph, the last line of that paragraph you will not understand if I did not do all these things. So this is actually first postulate of quantum mechanics. Okay. Any questions?
Sir,
Yeah.
in the simple example you gave to the left hand side, you have defined that 0 is not in S, but it is an open interval. So 0 will be there, no sir, isn't it?
No, in an open interval, the endpoints will not be there.
Oh, sir, then 1 is there, no sir. Then how 1 is there? You told 1. In the sequence 1, 1 by 2 is there. Then how 1 is a part of that?
Okay. So let me mark. That's a good observation. So let me say that this is half open, half.
Sorry, sir. Again,
I will put that one inside. Yeah.
okay, sir. That's it.
Sir,
Yeah.
is there any correct way to imagine Hilbert space as a structure?
I mean, what do you mean by correct way? Are you imagining it in a wrong way now?
Yes, sir. Can we imagine as a structure like real as we imagine in our mind?
Yeah, actually, this question is hard for me to answer because your mind is different from my mind. But what I'm trying to impress upon you is that when you say you want to imagine, your imagination is, I think, more or less restricted by 3 space dimensions. Okay, so since our experience is restricted to 3 space dimensions, our imagination probably is also restricted to these 3 space dimensions, unless others have a different view. This is my view because I could not imagine anything more than 3 dimensions. So anything which is higher dimensional or any abstraction which is of higher dimensions, I think we do not have to imagine at all. Why do you want to imagine some geometric structure for every space that you? So this is one thing which I think is a useful advice which I can give you, that in mathematics abstractions you only follow what are the operations that are defined. Okay, so you may have a desire to imagine, but then that desire should not actually stop you from making progress. Because any imagination where the imagination is not possible is going to give you a wrong imagination. Right? So that may be dangerous, and it may actually stop you from making progress.
Yes, sir. Most of the time it's wrong, as we know, as we lack knowledge about the phenomenon.
Yeah. So it is
Yes.
always better to stick to the rules of the game. Okay, so we know what are the rules of the game, and then play the game according to the rules.
Yes.
Yeah.
Excuse me, sir.
Yeah.
Sir, in the completeness of space, like we define sequence 5 1, 5 2, 5 3, 5 like so on. So I have like 2 questions. Like first is like whether they are the difference of 5m minus 5n, or they are something else. If they are something else, what are they actually?
So I have defined it. I have defined it here. So let us say that I have a sequence. So let's say I have phi 1, phi 2. These are all functions. Okay, phi 1 of x, phi 2 of x. So this is a sequence of functions. Now I am taking a phi m of x and then phi n of x. Okay. Now this is going to be some function, right? So let us call this function as some f of x, let's say. Okay. Now I am asking a question: what is the norm of this function? That means I'm going to talk about the inner product of this function with itself. Okay, and take a square root of that. Okay, now I am going to do this calculation for different, take any pair of these things at, so suppose I take one here and one here. Okay, so let us take these two pair and then find out what is this f of x. Then I take one here and another here, these two pair, and find out this one. So what I'm trying to say is, as I go farther and farther, this one will go to 0 as this n and m go to infinity. Okay, so what I'm trying to tell you here is operationally what we do it here, and physically what physically what it means is that they become closer and closer as you go farther and farther away. That means they crowd up. Okay, so initially maybe they are separated. This is with respect to this norm. This norm is induced by the inner product.
Sir, is this phi-m and phi-m kind of converging? Like that's why the distance is being decreasing. Can I imagine in that way?
Yeah. Correct. So that is why there is a limit point. They finally converge to that function, phi of x.
Okay, sir. And so is there any other function which govern this sequence? Like as you told, these are this kind of sequence. So most of the cases we have some pattern, or like suppose if it is by periodic function, then we have a period which govern its repetition. That then is there any such kind of function which govern?
That is probably I should say that if there is some property like period or something like that, that might define a Cauchy sequence. Okay, but if you ask, for example, some function which is periodic by a given period and all its harmonics will become a Cauchy sequence. But you can define a Cauchy sequence in general, and whether for every Cauchy sequence can you have something like a period is not very clear to me. I don't think we can find.
Okay, sir. Thank you, sir.
Yeah.
Sir, is completeness of space the same like correspondence principle?
Completeness of space is
like can we relate it means when n becomes large, the state becomes closer and closer, and in the end at much larger n it becomes one state. So can we relate it to correspondence principle?
no, I think we cannot relate it, because this property is even the limit point that we are talking about is also a quantum state. If you are considering set of quantum states of a system, okay, so the label of the sequence, this n that we are talking about, has got nothing to do with the quantum number.
Okay, sir.
Okay, okay, let me just think if there is a maybe. If you consider this as a sequence of okay, I am not seeing a connection at this moment, but I have to think a little bit. Maybe there can be some relation, because I'm thinking in terms of, let's say, if I want to consider a set of all eigenfunctions of some operator as a Cauchy sequence, then what happens as n? I'm trying to relate this n of the sequence to the quantum number, in which case maybe you have a point, but I am not very clear at this moment. Maybe I will think about it and then come back to you. There seems to be, I'm not able to deny that there is no relation completely, because you can probably think of a Cauchy sequence made up of eigenfunctions of energy, for example. Then in that case, as n goes to infinity, it makes sense to talk about correspondence principle. Okay, so I'm sorry, I'm not able to be very clear, but I will think about it and then tell you. There seems to be some possible connection.
Okay, sir.
Yeah. Any other question?
Sir,
Sir,
Yeah, one at a time.
sir, while defining vector space, we are taking
I'm sorry, Unnati, I could not hear.
audible,
Speak again.
sir.
Yes.
Am I?
Yeah, you are audible, but kind of piecewise discontinuous audibility is there. Anyway, speak slowly.
Sir, can I put the? Okay, sir. Sir, while defining the vector space, we are taking Vi belongs to complex number. So wave function is uh, defining in complex number space. So why we are in complex numbers
Yeah, so I think
in wave function?
yeah, so your question I think is why wave function has to be complex function, right?
Yes, sir.
Yeah. So I think in the past we have discussed this point from two standpoints. One is the structure of Schrodinger equation is such that it demands the wave function has to be complex value. And then we also, I mean, the other part I did not discuss in detail, but I said that the observed phenomena in nature, such as interference, okay, which is observed even with electrons, protons, neutrons, all kinds of particles, cannot be explained if the wave function is real. Because I think we discussed, I made a remark at that time that if you have double slit like arrangement, the wave function from corresponding to one slit and the other slit has to have a constant phase relation. And that relative phase will come only if the wave functions are complex. Correct? Otherwise, we will not have any relative phase. The relative phase will be either plus or minus. And that is not adequate to get maximum, minima in the interference pattern. So that is, so one I have argued from mathematical standpoint, the other one I am arguing from the physical standpoint. But one can actually do more rigorous argument, which I will give you later when I once introduce spin and Stern-Gerlach experiment and these things. Then we will try to give a very simple argument which will tell you that quantum states have to be complex value.
Okay, sir. Thank you, sir.
Yeah. Saubik?
Yes, sir. So the thing is that we talked about the square integrability and the square summability of the functions that we take in this Hilbert space. Because the sum has to be, the whole integration has to be a finite value less than infinity.
Yeah.
Then using that we can define it. So, sir, since it is a infinite sum, and we from that we are making an infinite integral. The limits are infinity to minus infinity. So doesn't that make it a like some restriction will be becoming on the function, because not all functions will obey.
Okay, I think I lost your voice.
So will it not give some?
So the last part of your question I did not hear.
Sir, I can. Sir, can you hear me now?
Yes.
Sir, actually, what I said is that the square integrability of a function is mandatory for the defining using it in this Hilbert space, as we have seen. So if all the functions that we use here are square integrable, then doesn't that give a very rigorous thing that only these types of functions are allowed to be used for this space, and other functions are not allowed, because
Yeah.
not all functions will obey that.
Yeah, that's correct. So what I'm trying to say is that if you have a quantum system, okay, let's say you have a quantum system, and the quantum system, so what I'm saying is the square integrable functions is the minimum that is required. Now, over and above that, suppose if you have a quantum system, let's say you think of a particle in one-dimensional box, this is your quantum system. Now you can say that there is a boundary condition that the wave function must vanish at x equal to 0 and x equal to L. Now this is an additional condition on this vector space. That means from the vector space of square integrable functions, you are going to take a subset of functions which will satisfy this boundary condition. That will become a Hilbert space for that problem. Okay, but minimum is L2. So if some function is not L2, we cannot use it. We cannot use it as a quantum state at all. So that is what I am saying. Suppose let's say we have a very let's say I like a function called e power x. Now can I use e power x as a quantum state for some physical system? Because let's say if your physical system is from minus infinity to plus infinity, I cannot use e power x or e power minus x for that matter. Suppose if the domain of my system is 0 to infinity, then probably I can use e to the minus x, but I cannot use e to the x. Like that, we have to choose these functions such that the square integrability is guaranteed. That is minimum. Above that, you have to also talk about the given boundary conditions that are coming from the physics of the problem. You may have a particle in a box with x equal to 0 and x equal to L, wave function going to 0, or you can have a situation where x equal to 0 is identified with x equal to L. This is called periodic boundary condition. So depending on the boundary conditions, we are going to have some subset of L2 or some other subset of L2 are going to be the state space of that function. So true, we are going to only work with a restricted set of functions because that is what physics demands.
Okay, sir. So this so for each different boundary conditions and each physical property of the system we are trying to define, we will get a new type of Hilbert space for each of them.
Exactly. That will be subspace of that L2.
L2 space.
Yeah.
Okay, sir. Thanks.
Sir?
Yeah.
On that day, I remember that I have two doubts. One doubt maybe can be relatable now. Second doubt, I don't know if you'll answer because it's something out of our syllabus out of now. The first thing is that on the day you told that we shouldn't physically imagine about a field and an operator, isn't it, sir? Like if we try to imagine, we'll be in trouble. But this is something which I had in mind. Like vector spaces can be thought of as a vector. The state space, the quantum states can be thought of vector spaces, and operators can be thought of some fields or some binary operations, something like that. And operating them over on a vector space will give us something like that. So I thought something like that. So is it like this?
No. See, binary operation that we are talking here is simply, that is why I always prefer to call this as a binary composition. Why I'm making this linguistic difference, even though operation and composition are interchangeably used, because of this confusion that might cause. Because what happens is when you define an operator is a different operation. It is not taking two elements of a vector space and combining them to get a third element. That is binary composition. Operation is like a linear transformation from vector space to itself. So that is different. So when we define operators in quantum mechanics and say that that is our second postulate we will go to, so there that operation is different than this binary operation. So we will restrict calling this binary operation as a binary composition. We take two elements, compose them to get the third element. Whereas operation, we will reserve that word to define operators. That is, a vector is transformed to some other vector by an operator.
It is more like a mapping than a...
Yeah, it's a linear mapping from vector space to itself.
Itself.
The second
Excuse me, sir.
Yeah. Yeah.
Like continuing to this question, continuing to this question was asked. Can I say that like wave function itself is a vector in some quantum space?
Yes, wave function is a vector in the Hilbert space. That is when I say state space, I have a Hilbert space, and wave function is a vector in the Hilbert space. Now the vector is a very general notion now. In fact, wave function you can call as an infinite dimensional vector.
Okay, sir. But then, sir, the second question, which was asked, like whether the binary operation can be a operator, then that also makes sense, right?
No. See, binary operation is what? Take two vectors and get a third vector by adding them, right? That is vector addition. Okay, but for a general operator that we will define later, we don't require two elements. That operator is one, and then every vector, when you operate that operator, you will get another vector. So it is a map basically.
Okay, sir. Thank you, sir.
Yeah.
I'll continue that, sir. We talked about that. This is some question which I asked, like why the energy states of a particle in a box is discrete, whereas in harmonic oscillator is continuous. So this was a question which was asked.
Energy states of harmonic oscillator are also discrete. No, why they are continuous?
Then I think I messed up the question. I'll get that question correctly, sir. Like that question was asked something like that. I'll get it.
Energy states of harmonic oscillator are also n plus half h cross omega. So n is different and they are also discrete.
Sir, from this question, another question coming. Sir, is the discreteness which comes from the energy of harmonic oscillators and which Planck has described. So is the discreteness built in the heart in the nature? Is the wave function, Schrödinger wave function is also discrete?
Wave function is not discrete, but see the discreteness in energy comes. We can show that it comes because of the wave nature of the particle. If the particles were not waves, we would not have got this discreteness in energy. So when we actually solve Schrödinger equation, you will realize from doing all that mathematics, at what stage of mathematics you get this discreteness of energy. So if you ask this question, you will see, just like what we discussed earlier, I said in response to Saubik's question, that you have L2 set of all square integrable functions, but depending on the boundary condition, you cannot take all the functions, you can only take a subset of functions. Now these subset of functions will correspond to only some discrete energy values. So it is this boundary condition that always gives you quantization.
Sir, so wave function is continuous, but if we operate energy operator, then we get discreteness. Is it correct?
No, what I'm saying is there is a discrete set of wave functions, but every wave function is a continuous function of x and t. But there are many wave functions, and this set of wave functions are discrete. Let's say psi1, psi2, psi3, these are discrete set of wave functions, but psi1 is a continuous function of x, psi2 is a continuous function of x, like that. That's what I meant when I say wave function is continuous. It is a continuous function of x and t, or space and time. But the set of functions, only those set of functions will become physically relevant wave functions for the system if they satisfy boundary conditions, right? So when we pick up that subset of functions satisfying that boundary conditions among this large set of square integrable functions, then we get this quantization.
Yes, sir, I understand. Thank you, sir.
Any other question? Okay, so just quickly give me some feedback. Is this going in an understandable way, or is it becoming too rigorous, because I have spent three lectures just to communicate one postulate of quantum mechanics, because there is a lot of mathematics involved. So should we continue doing this in this manner rigorously? One advantage of doing this rigorously is that you will learn this once and for all. You know all the intricacies of the subject. Other thing is, I can define all the 5 postulates or 6 postulates in one day, and then I can tell you, okay, this is how you have to solve Schrodinger equation, this is how boundary conditions are obtained. Then also you can still do some problems in quantum mechanics, but then maybe you will not have that deeper understanding. So quickly tell me, which one do you prefer? I can do both, there's no problem, but depending on your interest, I can switch my gear.
Sir, I think, sir, I don't know, like, we are enjoying this way, like, where we are learning more in deep and getting to understand, okay, how these postulates are formed and why they are formed. So I think that is more better and more interesting for us in order to appreciate this whole quantum mechanics.
Okay. So any other view?
Sir, we want to understand deeper, so this is helping us to understand, go deep in the heart of quantum mechanics. So we are enjoying.
Okay. So you're not finding it too rigorous or too tough, right? So,
sir,
you're not finding this too rigorous or too tough.
Sir,
Yes, Pranav.
actually, I'm not complaining about the rigorosity, but it would be easier if you just recommend us something to study the math from.
Okay. So essentially, I was trying to tell you that. So I mentioned about this book by R. Shankar, Quantum Mechanics by R. Shankar. The first chapter is completely on this thing. Then there is a 2-volume by volume 1 of Cohen-Tannoudji, 2-volume book on quantum mechanics. So Cohen-Tannoudji, and so this is first, the second, and then of course there is a book by Tulsi Das and S.K. Sharma. This is mathematics for quantum mechanics and classical mechanics. Classical mechanics and quantum mechanics. And if you want more rigorous, this Byron and Fuller. This is also mathematics for classical and quantum mechanics. And I don't know, there is an old book by mathematical physics by Chattopadhyay. And of course, I think there is I already told you that if you want to self-learn, there is a Sham series book on linear algebra. And then, of course, that mathematical physics by V. Balakrishnan. And that mathematical physics by Riley Hobson. So these are some books, but as I told you, unfortunately, I will not be following any one book like in the usual undergraduate courses. So it will be difficult to find what I am teaching from one book. But generally, these books are rigorous in the sense they will do much more than what I have done here. So you can pick up the relevant portions from these books. So that is the right way to study if you want to study from the book. So essentially, the aim of my teaching is that if you understand what I am teaching, any book will be easy to understand. So that is what I would say the advantage of attending this course. So that you can verify. You don't have to believe me. You can verify that if you take any book, then I think it becomes accessible to you to do problems or to learn from the book. Okay. Any other feedback?
Sir, you kindly continue like this, sir. Even if it is taking some time, we are learning everything. So from basic, so it's better to go in this manner. The pace looks great.
Okay. Okay, so if there are no other comments, and we can